Okay, so please join me in welcoming our next presenter, Vern Brownell, CEO of D-Wave, who will talk about the next wave of innovation in quantum computing.
So I have about 20 minutes to describe quantum computing, quantum mechanics, the business of quantum computing. So I'm going to go really quickly. But it's really a pleasure to be here, and thanks for the MIT alum group for inviting me. It's really exciting. So first off, why am I excited about quantum computing? Why do I think it's interesting, and why do I think you should be interested in it? Well, I think we have a couple of fairly existential problems in our computing environment into the future, and we've talked a lot about these today. The first problem is that, as we all know, our society is getting more complex, and we have all these sort of mankind scope problems that we have to solve, and computation is a core part of that. Yet, even some simple problems like folding a protein or doing an analysis of how a molecule really works or doing a quantum simulation of a material are beyond the scope of our classical computational capabilities today. And this morning, we talked a lot about autonomous vehicles, and I was really fascinated by the discussion. But did you catch the computational requirements that are necessary to build these classifiers and to build the technology that's going to drive those automated vehicles? It's amazing, and this is happening in all fields of human endeavor, I think. So we need more computational power to solve our future problems. The second is, you know about Moore's Law, and people have been talking about the end of Moore's Law for a long time. But we are starting to plateau out in terms of the computational capability that classical computers can give us. Lots of great novel hardware going on, lots of great designs, but still they're all classical devices. They're mostly CMOS processed, and they're all going to face these problems of tailing off into the future. So what's the answer there? The third problem is energy. And I built a lot of data centers in my life, and you all know the dirty little secret of the internet is how much computational power is in those data centers driving the internet. You know, go visit one of these data centers and see that firsthand. And that's only going to get worse. So these three problems, I think, are important, maybe not the only driver, but important drivers why quantum computing is important. So D-Wave, we're a little company based up in Vancouver, Canada. We are a leader in quantum computing. We've been doing this for 20 years. 20 years. I've been there for 10 years. But our mission really is to unlock the power of quantum computing for practical applications. Sounds obvious, but building quantum computers are really hard, and we'll talk a little bit more about that. The second thing is, I'd like to say, we say unlock, because quantum computing is really how nature computes. You know, you all, in your physics classes at MIT, you know that the universe works quantum mechanically. It doesn't work classically, it works quantum mechanically. So it makes sense for us to build quantum computers in the future to try to harness that capability that's just part of nature, unlock that capability of nature. So let's talk a little bit about how quantum computers are built. So we all know that the building block of classical computers is the binary digit, the bit. Sequential, we do amazing things with binary digits today, with bits, but they have limitations. The interesting thing about quantum computers, they're all built with something called a qubit, or a quantum bit. And a quantum bit has a property that it can be in multiple states at the same time. Sort of like this clicker is here and not here at the same time. It's kind of a mind-blowing thing to think about, but you know from your physics class, that's the way the universe works. You have a particle, you have an atom or whatever that's in multiple states at the same time. That's the beauty and the mystery of quantum. The other thing that with these qubits is they entangle with each other, so they influence with each other. And if you can engineer those influences, you can get some really interesting capability. It also, you can represent 2 to the n states simultaneously with n qubits. So there's an interesting exponential effect there. And if I can only get the clicker to work, okay. So there's a lot of different ways to build quantum computers. And there are a lot of players in the quantum computing space, and it's really amazing all the activity that's going on in the world. Our company decided to do a kind of quantum computer called a quantum annealer. And it's designed to solve hard problems. For the computer scientists in the room, the native problem that it solves is an NP hard problem. It does an optimization. It does really one thing. It does an optimization problem, a quadratic unconstrained binary optimization, or maybe some physicists in the room know it as an Ising model. And everything is built upon that one instruction, getting nature to do that computation. And the magic happens down in that chip that you see in that carrier there. It's about the size of your fingernail. It's a superconducting chip. It runs at very, very low temperatures, 10 millikelvin, minus 273 degrees C is the operating temperature of this. Let me talk a little bit how quantum annealing works, and this is just a metaphor, but many of you know what optimization problems are, and you can express a three-dimensional optimization problem as kind of a landscape. Think of the Alps, right? And what you're trying to do is get to the lowest valley in the Alps. Well, how do you do that? Well, classically, to get the exact answer, you have to kind of run up and down the Alps all the way with your little altimeter and then complete the entire landscape, and then you know that you got to the lowest valley in there, the lowest energy. The quantum annealing approach is leveraging nature again, but it's a little like a lot of drones kind of drop down into the landscape, and they can go down into those valleys, measure those altitudes, and then compare with each other who's got the lowest altitude. They can also do this trick called quantum tunneling. This is a little hard to visualize, but where they can tunnel through these energy barriers or these mountains to get to a lower one easier. So there are three properties of quantum mechanics that all quantum computers use. One is superposition, which is that ability to be in multiple states at the same time. The other is quantum entanglement, and the third is quantum tunneling. And those are sort of the capabilities that drive quantum computers and allow you to get this kind of capability. So the chip that I talked about in that carrier is actually in this big black box. It's 10 by 10 by 10. And the black box is really all to refrigerate and shield this little chip. It's got to run down at 10 millikelvin. It's got to have 18 levels of shielding so that it's almost a perfect vacuum. By the way, 10 millikelvin is 200 times colder than interstellar space. So this is a very rarefied environment. The interesting thing is we've been able to deploy these things in the field. We actually can put them into data centers, and they run for years at a time without any fault, which when I joined D-Wave, I thought this was a miracle to have something this exotic to run that long. But we currently have these in data centers, and we also have them, obviously as cloud services. I'll mention again, the superconducting nature of this is quite important, because one of the side effects of that is that superconducting circuits, as you know, don't generate any heat. There's no resistance in a superconducting wire. So as this processor scales up in capability, today we have 2,000 qubits, and we've been basically doubling that amount of qubits every 2 years, and not just qubits, but all the dimensions of performance. But as that performance scales, the heat that chip gives off will not scale at all. The only heat load in this is the actual refrigeration and the associated servers and things that kind of run the system. So very interesting. So let's talk a little bit about where we are today. So this is a bit of a cartoon graph, but and we have on the x-axis the hardness of the problem, the y-axis the computational performance today. Basically, where we are is that for benchmark problems, for a contrived synthetic problem, there have been partners of ours that have built a problem and run it on our computer and run it on the best classical computers with the best algorithms, and we can outperform the best classical systems with the best algorithms that are known at the current time for these benchmark synthetic problems. They're not really useful problems. What our goal is to solve customer problems. This is all about the kinds of customers that can use this kind of capability. And we are very close. Within this year, we will demonstrate customer advantage that otherwise, if you didn't use the D-Wave system, you wouldn't get the same result in particular problems, or by whatever metric you have, whether it's accuracy or energy used or time to solution or wall clock time. So you will see that. The other thing that I wanted to mention here is that Fundamentally, from a business point of view, there are two things that we're doing. One is we're making it easier to use. So we're developing and have developed a full stack to make it easy to use this system. And I encourage you, if you're interested at all, go to our website. You can get online with a quantum computer. You can self-sign on. We give you 1 minute of free time that you can explore how it works and actually get in there and run some problems. You don't even have to be a programmer. You can actually, there's some kind of interactive dialogues there. There's some nice Jupyter notebooks and things that you can use to try this out. So making it easier to use and then making it more powerful. This is our 4th generation of quantum computer. Our next one is coming out midsummer. And the systems that we develop will have more qubits. So the next one will be 5,600 qubits, denser connectivity, the connectivity between those qubits, which is very important for the hardness of the problem that you can solve. Lots of other capabilities that are important to the performance of quantum computing, like lowering the noise and reducing the latency, the I/O time in and out of the machine and things like that. So what's most important about a quantum computer, obviously, is what can you do with it? And this is what I'm most excited about, that we have all these partners and customers who have developed real applications. They're not yet at scale where they're outperforming the best of what you could do with the largest supercomputers in the world, but they're close. And they're in these 4 categories. Optimization, which is kind of the native problem that the machine solves. And that can range from radiotherapy to portfolio analysis to satellite placement, traffic flow analysis, internet ad placement, things like that. The next is in machine learning. And as we've talked about today, a lot of machine learning are complex optimization problems. Many of you know what a restricted Boltzmann machine is. This machine acts as a restricted Boltzmann machine natively. You're using nature to build a restricted Boltzmann machine. So some really interesting work there done. And then in the area of material properties and quantum simulation, this is what Richard Feynman had originally envisioned the quantum computer being able to do. There's been some really good work there as well. And cybersecurity and fault detection. So those are rough categorization of the kinds of problems that we solve with the problem today, with the computer today. So let me go through a couple of these. We have our customer list is partially there. We have about 40 cloud customers, paying cloud customers. We have 3 systems that are actually installed in the field. One is up here at NASA Ames. We have one at Los Alamos National Labs, and Lockheed has one down at USC as well. So Volkswagen is an example of an early customer. They've done some interesting things in the mobility space. The first application they used our machine for was actually optimizing traffic routes for taxi cabs. And they had some data from Beijing that they used and developed an optimizer using our system. And they've taken that forward. And actually, I'm going to Lisbon in a couple of weeks as a presentation with the CIO of Volkswagen to announce the next step that they've taken in this traffic flow optimization. They hope to build this into a service that Volkswagen will get into at some point. They're also doing battery research in the area of material science that we talked about as well. Denso is a very large Japanese-based parts manufacturer. This application is optimizing automated guided vehicles on the factory floor. So they built an optimization framework, and they were actually found that they could get 15% better performance, average time, as well it says here, spent waiting a clear route open by an average time of 15%, even when focusing on safety over speed. So the idea is that there are all these vehicles running around the factory floor, and there's an optimal flow to balance the number of stops that they have to do while clearing another vehicle. And the goal is to try to deliver as much of the material that they need to on the factory floor as efficiently as possible. A third application in a very different vertical is Wuxi Nextcode. They're a proteonic or multi-omic data company in Cambridge. And basically, they have built classifiers using our technology. This is an interesting example of one, which is a classifier to distinguish between luminal A and luminal B breast cancer. I don't know much about luminal A and luminal B, but they were able to train a classifier with just 34 patient samples. And we talked about the importance of being able to train with very little data. I think this is a good example of that. So they're actually, the top line there is D-Wave, and they're very much able to get good results with a very small amount of data. Another important one, from our perspective anyway, is the work that we published in Nature and Science last year in material simulation. And this is a fairly exotic paper. It's talking about phase transitions in topological matter. Michael Kosterlitz won the Nobel Prize for this in 2016 for the theory work. And he said this paper represents a breakthrough in the simulation of physical systems that are otherwise essentially impossible. What I really think is exciting about this is you can actually model and simulate materials that don't exist. And then you could start to examine what those properties are. You think about what the future is in terms of being able to build more efficient fuels or lighter materials or things like that. This, I think, is going to be a breakthrough area for quantum computing. So to give access to this, we're spending a lot of time trying to build a developer community. So the first part of this is access. So as I said, there is a free offering where you can get your 1 minute a month of D-Wave time if you're interested in using a quantum computer. It's available 7/24. It's real time. You run a problem, it'll hit the quantum computer and give you a result back. There are lots of pedagogical examples in there, lots of learning capability videos to kind of guide you through quantum computing. So I encourage you, if you have interest, please go on there. You can actually renew that 1 minute a month if you contribute to the open source community. If you give us your GitHub handle, we'll continue to give that 1 minute a month. That's about 3,000 problems that you can run on the quantum computer for that 1 minute a month. So where are we today, and maybe what are some recommendations of how we move forward? So one important thing that's just happened in the last few years is that there are now real implementations of quantum computers. Prior to us and other companies, there were just theoretical notions. But you can go out today and go to IBM's quantum computer. There's a company up in Berkeley called Rigetti that has a cloud offering. And you can go to our computer, right? And you can use these quantum computers and explore what you can actually do with them. That's the first time in history that capability has been available. And it's really good for us because frankly, we don't have to compete with theoretical notions of quantum computers. You can go try running problems on the IBM machine, and you can try running problems on our machine and see what the difference is. And if you have interest, I'd encourage you to do that. But a trick is, quantum computing is not for all kinds of computing, right? It's really, especially in the early stages of it, you have to identify what the best problems are, or the core problems that you're trying to solve. And so that's where a lot of the training and the use in the cloud will help you determine that. And then, of course, you'll have to learn how to build these quantum applications. One thing I should mention is that don't think of quantum computing as a replacement for classical computing. My belief that the future is really a hybrid world where we have all forms of computing together, and you're using the right resource for the right types of problems. And in fact, one of the things that we're working on and have done an announcement about is a hybrid approach where you basically, we will use the right classical resources alongside the quantum resources at the same time to make it easier for a developer to use this kind of capability. But I do think it's time to get started. It's happening, it's real. There's lots of activity. I mentioned Rigetti and IBM and ourselves. We're the only ones that actually have cloud offerings that you can actually use, and we have free offerings. But as you know, Google and Microsoft and Intel and Alibaba and many other companies have their own quantum computing efforts going on. So the next decade, you're going to see a lot of activity. It's already ramped up pretty dramatically, and it's a super exciting space to be in. So I have only 30 seconds left for questions, but I'd be happy to.
Is quantum computing applicable for things like modeling the effects of climate change on the atmosphere and the ocean currents and so on?
It certainly could be. We don't have any customers that are doing that sort of work right now. I have talked to someone at Woods Hole Institute in Cape Cod that's doing some work in modeling plastic flows in the ocean and some of that sort of work. So I assume, I hope that it's applicable to some of those human scale problems as well. Any other questions? Great. Well, thank you so much.